My name is Matt Knight. I'm a software engineer with Bastille Networks, and today I'm going to be talking about this new wireless protocol called LoRa. We'll get into that in a minute. I love electronics and wireless. I've came from a EE background, work mostly with SDR these days. This is my passion, so I'm excited to be here. I also want to give a shout out to the Wireless Village people. I've absolutely haunted this place for the last 4 or 5 DEF CONs, and I'm really excited to be here and present for you guys. Okay, before we get started, this is going to be more of a FI radio talk than like a security talk. No 0 days, no exploits, but we are going to look at a very low level into a brand new cutting edge protocol. So before we get started, just want to gauge the room. Hands up if you've used an SDR before. Okay, good. If you've used a spectrum analyzer. All right, cool. And you know what an FFT is? And who knows what a symbol is in the wireless context? All right, cool. All right, so why is this relevant? Why do we want to look at a low level at these different radio PHYs? Cisco projects that by 2020, there are going to be 50 billion devices connected to the internet in some way, and fewer of those are going to be connected with wires every year. And in terms of security research and having insight into what they're really doing, we need to develop tools to be able to stay ahead and really be curious about these things. Because Wireshark existed because somebody made it, and monitor mode capable Wi-Fi cards weren't always a thing. So we need to make the tools so that we can do this low-level introspection and stay ahead of the game here. So I'm going to introduce this new class of network called LPWAN. I'm going to review some technical concepts, and then we're going to get really low into the LoRa PHY and talk about how it works. Finally, I'm going to introduce an open source tool that's coming out soon, and we'll hopefully get this into more hands. Before we get started, everybody's favorite marketing buzzword right now is IoT, Internet of Things. And I kind of resent the term because really it's just fancy speak for connected embedded devices. Okay, how's that? All right, so embedded can mean a number of things, but a common theme is that there are hardware constraints involved. You often have low intelligence CPUs. They're battery powered, so you can't do complex operations on them. They get installed in hard to reach places. They need to last for a long time. They might not get patched. And they do often require installation and provisioning. You have to have somebody go, put them somewhere, and change some settings to get them to connect. So given this, an ideal interface, if we could design it, would be wireless, so you don't have to run cable to it, easy on the battery, so it can last a while, capable of being installed anywhere, whether it's in the middle of a field or in a building in an urban environment. No configuration, easy to provision. You don't want to have to type in an SSID and a password to get it on Wi-Fi, or pair it with the coordinator, need a gateway on site or something like that. And finally, it would be inexpensive. Now let's talk about what's not required. And oftentimes when you're connecting devices like this, high throughput and persistent and always on connections are often things that we don't really need. If you have a sensor that you're just trying to report some data off of GPS every 10 minutes or so, it doesn't really require an LTE pipe to do that. So as it currently stands, IoT devices are grossly overserved by some of the common interfaces that are out there. So when we talk about IoT interfaces, we're often talking about things like 802.15.4 and all of its friends. Zigbee is a layer 3, an up flavor that people confuse. But 802.11, Wi-Fi gets used a lot. We have Bluetooth low energy, etc. So what's wrong with all of these? We have these standards. Why don't we use these? All of these protocols that we talked about require some local provisioning. Whether it's Zigbee, Zigbee or 802.11, you need to connect to a coordinator. If it's Wi-Fi, you need to get on an AP, etc. In the case of 802.11, it's not too power efficient. So what's ideal then? What if you want an application where, say, your device is moving around? You're monitoring a vehicle fleet that drives throughout a city or across the country. Or if you want to monitor fuel tanks. If you have heating oil tanks in New England and you want to remotely report back on their level on how full they are. You don't want to have your installers having to go and get on the home Wi-Fi of everybody there. How about cellular networks? They work everywhere, and they're easy to install, pretty much guaranteed. One big problem with them is that they're very power intensive. And a second problem is that some of these PHYs are going away. So 2G in particular, AT&T is scheduled to sunset it at the end of this year. So January 1st, 2017, they're turning off their GPRS and Edge PHYs. And other major carriers are going to follow. These networks are really popular for a lot of these IoT applications because they're battery conscious, you get service everywhere, and they're somewhat inexpensive. So if you are a company that is deploying a device on a GPRS or edge network now, what are you going to move to? You can move to 3G, which is a little more expensive and has some harder power requirements, or you can wait for this thing called LTE-M Release 13. It's part of the LTE standard, and basically it's going to allow for devices to use narrower bandwidths and lower data rates to get some of these higher performance applications for long-term embedded applications. However, the roadmap as it currently stands, at least what I've gleaned publicly, is that that's not going to be deployed until the end of 2017 or early 2018. So until then, there's a big hole in the market for these embedded devices to connect. So that brings us to the topic that we're going to discuss today, which are these low-power wide area networks, LPWANs. The way to think of these things is they're just like cellular, but optimized for IoT and M2M applications. So you have a network of base stations that are deployed over some area of coverage. It could be local, it could be a city, it could be the entire world. And then devices connect up to them as they would in a star network. So you have these central base stations, and then devices and nodes connect directly. There's no meshing, no routing, just device wireless link to the base station. They can uplink and downlink traffic in many cases, and they have a range typical of miles. So again, really think of this just like being cellular, but for low data rate applications. There are a whole bunch of standards that are popping up, but the most popular ones, or the ones that have the most momentum, are LoRa and Sigfox. They've raised a ton of money in the last 18 months or so. Sigfox raised $115 million last year, and Wall Street Journal reports that they're going to IPO. So they're growing like crazy. Raise your hand if you've heard of them. Not too many hands. And finally, two companies that are big LoRa backers raised $51 million last year. So there's a ton of investment. Investors see the relevance here. So expect to see these protocols being more and more relevant going forward. Let's talk about the stacks and what makes them cool. As I mentioned, they're optimized for IoT applications, meaning they're very battery conscious. That's probably the big thing. Sigfox, one of those standards I just mentioned, gets 10 years on a single AA battery. That's what they advertise. That's like pretty crazy to be sending data over miles for 10 years on a single AA. You cannot do that on LTE. And LoRa advertises 13 miles of range between the end node and the base station. So pretty crazy coverage. Compare that with like 2G, which has a limit in the standard of 22 miles. All these other things are really local, short range, and they are not great on battery. So this is a huge step forward for embedded devices. How can they do this? They embrace the fact that embedded and IoT applications can accept some level of compromise. So they embrace this, and they duty cycle the messages heavily, so you're not sending that much traffic. You're often not always listening all the time, so you might have scheduled windows where the end device will wake up and keep the radio on. Look for downlink from the base station. Really small payloads. We'll talk about that in a minute. And they're very highly rate limited. So some examples. Sigfox limits devices to 140 12-byte datagrams per day. Think about that. That's like, what is that? That's like a single UDP packet. And finally, weightless N is uplink only, so it can only send messages up to a base station. It cannot accept messages down. And finally, LoRa Class A devices only can receive a downlink message from the base station after sending an uplink message, so they're not promiscuously listening. So this is quite different, and there are some really unique features that contribute to this. So the rest of the talk, we're going to spend talking about one of these LPWANs in really great depth. We're going to talk about this PHY called LoRa. LoRa is an LPWAN PHY that was developed by a semiconductor company called Semtech. It was actually developed by a startup that was acquired by Semtech, but Semtech is the company that's evangelizing it and pushing it worldwide. The PHY was patented in 2014, and the first definition of the MAC and network stack that they're pushing products on came out last year. So these things are brand new. They really haven't been battle tested, and are just starting to become available. Just to clear something up before we continue, oftentimes you'll hear the term LoRa used. Sometimes you'll hear about LoRaWAN. LoRa refers only to the PHY layer, and LoRaWAN is the higher layers built on top of it. So think of it as being like 802.15.4 versus Zigbee, different layers of the stack that often get used together. LoRaWAN defines a whole bunch of security features. They've done a pretty good job of thinking about these things ahead. But some interesting features is that the MAC stack is controlled by an IP-based network server. that does all of the intelligent coordination in place of the base stations. Probably do some more on that later if there's time, but they also define the security architecture that does enable a unique key being used per device, but that's left up to the application to implement, of course. And they also have two different keys. So you have the application key, which is end-to-end between your company's application server and the end node, but then there's also a network key that protects everything going from the end node to the network server. So if you're a developer, you can use these application keys to make it such that the carrier never sees your content in plain text. That's all we're going to say about LoRaWAN. We're going to talk about the LoRa PHY from here on out. So one of the really unique things about this PHY is that it operates an unlicensed spectrum. So when we say unlicensed, we're talking about the ISM bands in the US, primarily 900 megahertz and 2.4 gigahertz. And in these bands, you have devices like Wi-Fi, 802.15.4, cordless phones, etc. You don't need a special license to operate on those bands so long as you abide by certain rules and regulations that the FCC has put out. If you go to Best Buy and you buy a router, you don't need to petition the FCC to install it in your house. You can just do it. It's because Netgear or whoever you're getting your router from plays by the FCC's rules. They get it certified, and anybody can use it in mass market. Contrast this with cellular, right? Cellular operates on private and protected spectrum that is very expensive. The FCC auctions the air rights to the spectrum for billions of dollars, which restricts building infrastructure to the biggest companies, Verizon, AT&T. You can't legally put up your own 4G base station in your house if you wanted to. You'll get a phone call. So I don't know if you can see the numbers here, but this is a price list from the FCC's reverse auction of some very high-value wireless or TV white space spectrum that was recently auctioned. Circle one number there. You probably can't see it. That is $900 million for WCBS TV in New York. So if you want to start a cell network, maybe we can pass the hat and buy some spectrum at the end of the con. So there are a couple companies that are building up cellular-type networks on this LoRaWAN technology. The two big ones are Senate, which actually started with that heating oil monitoring scenario that I mentioned earlier, and now is doing a commercial data network, kind of at scale. And the Things Network is another one that's really interesting. That's a totally crowdsourced network. So they own a couple base stations here and there, but really what they do is they provide that network backend architecture open on the internet so that anybody can buy their own LoRa hardware, set it up wherever they want, and then send the data back to their network servers. So think about how radical this is. You don't need a spectrum license to stand up a base station that can cover miles and miles of range. One day you might be able to go to Best Buy and buy a LoRaWAN gateway and stand up a network that either could be private or could be hooked up to something like the Things Network that could cover, all of Manhattan, right? That's really cool, and that's like a pretty radical shift for connected devices and IoT applications going forward. Okay, so we're going to run through this next section. I figure it's on the first, technical talk of the session here at the Wireless Village in DEF CON. We might have varying levels of experience. Let's just kind of even the playing field a little bit. This is going to be obscenely short, so bear with me here. We're talking about the PHY layer for the rest of the talk, which is this lowest level on the OSI stack. And that refers to how bits of data get mapped into the physical electrical characteristics that are used to carry it. So we're talking about voltage, current, actually moving electrons. So that's where we're going to be moving forward. We're talking about a wireless protocol which travels over radio frequency, and that's just electromagnetic waves and energy moving through the air. And you can manipulate RF by using a radio, which can either be hardware defined, like a chip that speaks one protocol really well, or software defined, where you have really flexible hardware at the front end, and then you implement the hardware and protocol specific stuff in software. Really flexible and allows you to iterate and prototype things really easily. When we talk about radio PHYs, one of the most important components is this thing called the modulation. And that defines how the digital data values get mapped to RF energy, how you take the bits and convert them into signals moving through the air. And when you're modulating, there are three parameters that you can play with. You can play with amplitude, frequency, and phase. Or you can put them together and use some combination. Modulators can be either analog or digital. With digital modulation, we have this notion of something called a symbol. And a symbol is an RF energy state that represents some quantity of information. It is discretely sampled. We're going to get into this more, but just think about this concept of a symbol being a state that represents data. We're going to talk about it more going forward, so just remember that. To illustrate some symbols here, we have two different IoT, common IoT PHYs. On the top, we have frequency shift keying. On the bottom, we have on-off keying, which is like an ASK type thing. And on the FSK example, a symbol representing a single bit of information is a frequency being on, or is the power being on one frequency versus the other at some instant in time. And with the OOK example, it's the presence of the signal. So these are all different, how different modulations represent digital information over the air. There are some more complicated PHYs that are used as well. On the right there, we have an 802.15.4 packet, and what 802.15.4 does is it spreads its information across a wider, it spreads its information across more spectrum to increase resiliency and get some low power features in there too. Makes it more resilient to RF noise and interference. And some other more complicated PHYs are Bluetooth and Bluetooth Low Energy that do some frequency hopping and things like that too. So we mentioned hardware and software-defined radios earlier. We're going to use one of each in this talk. On the top, we have a hardware-defined LoRa module. That's what I use to generate the traffic that we're going to take apart. And on the bottom, we have a really popular EDIS B210, which is a commodity software-defined radio that we're going to use to prototype our receiver and iterate quickly on this protocol. Last thing I want to talk about is a fast Fourier transform. What this does is if you feed it some samples, it will decompose the signal into the component frequencies that comprise it, and we can visualize this using a spectrogram. So here we have a whole bunch of FFTs that we've run over a signal in time, and then we have time in the y-axis, the frequency increasing in the x-axis, and finally power in the z-axis, how intense the signal is there. We're going to be seeing some more of these. So, okay, cool. That's enough with the crash course. Back to the main event here. LoRa implements a proprietary PHY that's built on a modulation called chirp spread spectrum, CSS. Now, what is a chirp? A chirp is a signal that is continuously increasing or decreasing in frequency. It's like a sweep tone. We have some visuals here. An up chirp is on top, and here you can see the frequency is linearly increasing until it hits the edge of the band, and then it wraps around to the bottom of the band and continues increasing, right? The frequency can change instantaneously, but the rate at which it's changing is constant, right? The first derivative of the frequency is some constant value that's going up. We can have the complex conjugate of that too, which is the down chirp with the frequency decreasing. So just keeps going and then wraps when it hits the edge of the band. Why would you use CSS to carry data? It's very resilient to interference and gives you great, link budget, multi-path performance for real-world deployments. So it provides some benefits. It's pretty interesting. Where else would you see something like this? And answer is radar. CSS features are derivative of some RF elements that you often see in radar systems. Just some examples here. Marine radars will use chirps for their ranging applications. Also, chirps are used in some scientific and atmospheric radars. And there's an open source project that's pretty interesting that has some really cool visuals online if you want to check it out, of chirps being received that had been reflected off of the ionosphere to measure space weather and geomagnetic activity. So that's pretty cool. So I first heard of this LoRa protocol in December of last year. I thought it was pretty cool, so I went to look for it. I got my SDR and went on a little fox hunt. I couldn't find LoRa in Boston, Atlanta, San Francisco, or New York, pretty big engineering urban centers. However, a few weeks after I heard of it, I ran into this company, Senate, at a meetup in Cambridge. They were talking about their company and their network, and one of the things that they mentioned was that they were from, one of the things that they mentioned was that they were growing pretty rapidly. So I was watching one of the marketing videos, and they popped up this pretty slick graphic. Looks like a coverage map, right? And I look a little closer here, and where is that? That's Portsmouth, New Hampshire. So at the time, I was living in Cambridge, Mass. Portsmouth isn't too far away, so grabbed my radio, went for a little drive, and here I am sitting in my car, USERP on the dash, and the result of this little field trip was some LoRa found in the wild. So luckily that graph they showed was that was real live data on their deployment. The base stations that were on that picture were real. So there you go. So let's take a closer look at this random signal that we captured in a parking lot in Portsmouth. This is part of the PHY frame that we pulled out. Some features we can immediately identify is up at the top, we have some continuous repeated upchirps. So the signal is just increasing kind of continuously. Then finally, about halfway down, we have, we can think of that as being like a preamble. Finally, halfway down, we see the chirp direction changes. We have two down chirps, which looks like a start of frame delimiter, some sort of synchronization element. Finally, after that, we have these choppy upchirps of varying length. So again, notice the frequency is always increasing, although it might change instantaneously. So the rate of change for the frequency is always constant in that PHY data unit, but the frequency might jump within that band. And that's how we modulate data onto this waveform. So yeah, we just talked about that a little bit, jumped the gun on the slide. But one way to think about the way that data is encoded is it's kind of like frequency modulated chirps, right? The chirps are kind of your signal that you modulate, and you modulate it by changing the instantaneous position within the band. So let's take this thing apart and try to get the data out of it. So LoRa is a closed PHY. It's proprietary. The spec is not published. The LoRa WAN spec that defines the MAC and network layer, that's open. You can look that up. But the actual modulation is closed. And that's because Semtech, they make ICs. They don't want other people knowing how it works. But there are some documents out there that leak a little bit of information that we can use to start gauging our exploration here. They have a European patent application which talks about some very high-level concepts. They have that MAC and network spec which talks about PHY elements without necessarily going into too much detail. We have some application notes which talk about some radio-specific considerations. That's if you have one of their LoRa ICs, some of the features that they implement. And finally, there's a little bit of prior art out there. There was an open source project called RTL Strangelove that had an attempted LoRa decoder. I never quite got it working, but there were some good hints there. And finally, some pretty high-level observations on the PHY on a wiki page. So from all this documentation, we're able to start to pull out some definitions about features that are actually occurring in the PHY. We have the bandwidth, which is the width of the chirp, how much frequency the chirp traverses if just allowed to run continuously. Secondly, we have this notion of the spreading factor, and this is very important. This is a very important concept that we'll talk about. The spreading factor represents the number of bits encoded per symbol. So this is a spread spectrum modulation, meaning that we have multiple bits being encoded into each symbol. So the spreading factor is the number of bits in each RF energy state that we're going to measure. And finally, we talked about the chirp rate. That's the first derivative of the frequency. All of these things are mathematically defined, and from these documents, we can start to figure out how they relate to each other. The bandwidth in the US is 125, 250, or 500 kilohertz. The spreading factor ranges from 7 to 12 bits per symbol, and finally, the chirp rate is a function of the first two. So, if we know the modulation parameters, we can figure out what the chirp rate is. So what's a symbol in this case? We mentioned it being a frequency modulated chirp, but what we're going to be trying to do when we demodulate this is measure the changes in frequency throughout the band as that chirp jumps. All right, so here's our little checklist here. When we're writing software to find and decode this, there are a few steps that we need to do. Pretty much all digital radio systems have a preamble and a start of frame delimiter for training the receiver to pick up an incoming message. So the first thing we're going to do is we're going to find the preamble, which is those repeated upchirps at the beginning of the frame. Then once we have that and we think we're about to receive a packet, we're going to start looking for those two downchirps, which we're going to use to synchronize on the start of the message. Finally, once we have that, we're going to extract the data from the frequency transitions by doing some math. So how can we do this? One technique that I found that was pretty cool was if we do a little transformation on the signal, it puts it into a form that makes it pretty easy to work with. So we can de-chirp the signal by generating a local copy of each of those two chirps and multiplying it against the original baseband. And we know what the chirp rate is because there are a finite number of modulation parameters. We can kind of guess them until we get the correct chirp rate, which is just a function of those two features, spreading factor and bandwidth. So we do that, and we start to see something interesting here. This is just an IQ signal being run through a GNU radio flow graph that does this. So some repeated elements here. Don't know if you can see it. We'll move quickly through this and look at a better picture in a minute. But here we can start to see that those chirps that were previously, diagonal moving throughout the spectrogram have been rotated and are now vertical. And that looks like something we can start to play with. So going back to symbols, we know that the symbol is the energy state representing how many bits of information there are. And since LoRa's spread spectrum, there are multiple bits per symbol. We can derive from this the number of possible symbols that there can be, and that's just 2 to the spreading factor, because each bit can either be a 1 or a 0, right? And that's just how it works out. So we can leverage this to come up with a method for extracting symbols from this de-chirped signal, and we can do that using a fast Fourier transform. If we set the width of the FFT, that is the number of component frequencies that we're looking at, and run the de-chirped signal through it, then each bin will represent a possible symbol, and then the symbol which is present is just the bin that has the most amount of energy in it. We'll illustrate this in a minute. So here's our original signal next to the de-chirped signal. Again, chirp can either be positive or negative, up chirp or down chirp. So when we do the multiplication, we do it against both, and we get out these 2 different IQ streams. So on the left is the de-chirped up chirp, and on the right is the de-chirped down chirp. So you can see that the preamble and the data, which are always up chirps, are going in the right direction, and the those come out when you de-chirp the up chirp, and finally the SFD, those 2 down chirps, you can see as a pretty intense little red spot right there on the right. Going back to our flow graph, we need to start working through this process and actually writing software that does this. So identifying the beginning of the packet is signified by finding this preamble. And the preamble in the case of LoRa is the same symbol being transmitted over and over again. Remember, it's just that continuous up chirp. So when we de-chirp it, all of that energy winds up being in the same FFT bin. So we can do this and just look for a number of consecutive symbols having the same value, and that says, okay, we're probably getting some data out of this. We're probably about to receive a packet. Finally, once we've found that, we need to start looking for that synchronization word that we're going to use to lock onto the start of the packet. And we do that by looking at the opposite de-chirped signal. So again, remember, we found the preamble in the de-chirped up chirp signal. So we're now going to look at the de-chirped down chirp signal and look for that SFD. And in the LoRaFi, it's I found it to be 2 symbols. So we just look for 2 symbols that have the same value, and then we can use that to synchronize. We're missing something important here, and that's that SFD detection is essential for having accurate synchronization. And if we have a bad sync, in this case, what can happen is we can wind up spreading energy between multiple consecutive FFT bins. And that can lead to reading the data out incorrectly. Here's an illustration. If you look at these bins that I've pulled out, we have element 39 and element 50. You can see that there are basically 2 peaks in each of those FFTs, right? Ideally, we should just see 1 because there's only 1 symbol, because we're reading out 1 symbol per FFT ideally. So basically, what's happening here is we have multiple symbols leaking into each FFT. You can think of it as if you have a buffer, and each symbol is 2 to the spreading factor number of samples. In this case, it would be 56 because this is an SF8, spreading factor 8 signal. You can think of it as being that 128 samples in that buffer are from symbol 0 or symbol n, and then 128 samples in that buffer are from symbol n plus 1. So we need to basically realign that and get it so that all 256 samples in that FFT are from 1 symbol. So one way we can do that is we can increase our FFT resolution in time by overlapping them. So basically what we do is if you have your FFT buffer, you kind of walk it through and process each sample multiple times as it traverses through the buffer. And this has the effect of getting you better resolution in time. So we overlap the buffers, and we get this nice picture on the bottom here. On the top, we have a non-overlapped FFT, same picture we saw earlier with the collisions. And on the bottom, you can see that those features start to become much more defined. So if we do that when we're looking for the SFD, this is the overlapped FFT, zoomed in a little bit. Here it is. Looks much cleaner. So if we overlap these FFTs when we're looking for the sync word, we can get a very precise, we can very precisely calibrate our receiver to that and read the data out correctly. So here are all 3. On the left, we have the non-overlapped. In the middle, we have the overlap FFTs, and on the right we have the synchronized the synchronized non-overlapped FFT that we compute after we find that sync. So we'll zoom in just a minute here. Look at line 39 there, 38 and 39. Look at how much better that looks. I know there's some noise in there, but you can see where the maximum is, right? It's much cleaner, much more defined. So there it is. We went from the unsynchronized to the synchronized, and we get much better precision out of that. Finally, step 3, we need to extract the data, the data from the payload section, which we'll get to in a minute, and then we normalize it about the preamble. So if we take whatever bin the preamble occurred in as being data element 0, then then we can just rotate the data values within, or relative to that, normalize it, and we're good to go. That's it, right? Hardly. We're just getting started. That's the demodulation. And the data that's being sent over the air is being encoded. What is encoding? Basically, the data gets transformed before it gets sent to the demodulator to increase the over-the-air resiliency of the signal. Why would you want to do this? Why would you want to add the complexity of adding this encoding onto your signal? Well, a smart guy once shared some information with me. Is he here? You should talk to him. He knows a lot. I didn't quite understand this at the time, but I think what he was getting at is the fact that radio frequency is a really brutal environment to operate in. All systems can see interference from the environment, whether it's weather, other devices, and then add in the fact that this PHY is designed to operate in unlicensed spectrum, where you're guaranteed to have lots of other traffic, right? You have to contend with Wi-Fi, you have to contend with Bluetooth. If somebody is microwaving their leftovers, that's going to produce some emissions in 2.4, and that's going to interfere with you, right? So encoding scrambles and replicates the data within the frame to increase resiliency. So what do we think we have here? Let's take a closer look. We have some clues from those documents that we looked at earlier. Specifically, the patent suggests that there are 4 stages of encoding being applied here. First, we have this thing called gray indexing, which adds error tolerance for off-by-1 symbol errors. So if when you do that FFT on your D-chirp signal, the power accidentally registers as being off by plus or minus 1 bin, the gray coding will correct that when you apply it. Secondly, we have data whitening, which induces randomness, lots of little transitions for your receiver to synchronize on. Third, we have interleaving, which scrambles the bits within the frame, just takes all the bits that are there and moves them around. We'll talk about that in a minute. And finally, forward error correction, which adds correcting parity bits. So we have some, from our open source intelligence, we have these 4 distinct operations to reverse. So when the order that's being presented here is the order that the receiver is going to process them in. So the receiver would start with step 1, go through 2, 3, and 4. The transmitter does the inverse. So steps go 4 through 1 when the transmitter is preparing this data. But again, we're reversing this, so we're thinking about this from the receiver perspective. Now, I'm going to go a little bit out of order here, and I'll explain why. I'm going to start by explaining the forward error correction. The reason why is because the forward error correction is essential for reversing the other steps. We're going to exploit some properties there that make the other steps a little easier to understand if we can understand what the FEC does to the data before it gets sent. So forward error correction, you can think of it as being like parity bits on steroids. They are parity bits that, in addition to detecting errors, can repair them. A common FEC scheme is the Hamming scheme, where depending on how many bits you have, there are some little rules that define how many bits get you a certain amount of tolerance. You can repair errors. So if you have, let me explain these numbers here. So we have 2 pairs of numbers in each of these different modes. The first number is the total number of bits in the encoded data code word, and the second number is the number of data bits that get input. So the difference of the 2 is the number of error correcting bits that get added. And if you have 1 or 2 error correcting bits for 4 data bits, you can compute parity, just like having a parity bit in like RS-232 or something like that. But if you have 3, then you can go a step further and correct an error bit. And then if you have 4 parity bits, in addition to correcting that bit error, you can detect if there were 2. You can't correct 2, but you can at least know. Okay, so Am I missing a slide here? No, I'm not. Okay. So we're gonna come back to this later, but just remember that when we're talking about FEC, we're adding parity bits to the data bits. So you're increasing your data size as you apply FEC. Okay, so going back to that flow graph, right? This is step one, the gray indexing. The patent suggested that gray coding was applied to the signal before it was sent, and in fact, experimentally, it was determined that the gray encoding was actually the reverse. The payloads that were sent were degrayed before they went over the air. And we were able to determine that experimentally but while working on the whitening. And again, the whitening is that step two, which induces the randomness into the data. So the way the whitening works is the transmitter will XOR the data against a pseudo-random sequence that is known to both the transmitter and the receiver. So this basically takes your data, applies it to some mask, and then sends it. The receiver will then XOR the received data against that same pseudo-random sequence. And that will return the original frame because XOR is its own inverse. Why would you want to do this? Randomizing the data or add some features to it that make it easier for the receiver to lock onto. You can think of it as being like line coding, like Manchester encoding. However, whitening has an advantage in that it doesn't reduce the effective bit rate that your signal can use. Manchester imposes a penalty of, I guess, your effective bit rate becomes half of what it would be if you weren't applying Manchester encoding. Whereas whitening, since it's just an XOR, there's no penalty there, no overhead. So we had to find this whitening sequence to know what to XOR or receive data against. There are a couple of different whitening algorithms defined in one of those reference designs, one of those application notes I mentioned. Also a few that were published in RTL Strangelove, that open source project. However, none of them worked. I implemented them all. I tried them against the received data, and it just didn't make any sense. However, we can again go back to our friend the XOR operator and start to do something clever to back this out. One awesome property of XOR is that if you XOR data against a string of 0 bits, you get the data out. You get the original data out. So if we transmit a frame of all zeros, from the transmitter's perspective, the receiver is going to get the whitening sequence out of that. So that's kind of cool, right? Yeah. So we're going to do that, and some things that we can that help us get this right is we mentioned the Hamming correction. Hamming 8.4, all of the code words contain 4 1 bits and 4 0 bits, except for the code words for data 0 and data F, right? And the code word for data 0 is just all zeros, so there's no FEC being applied here, so it doesn't mess with our receive whitening sequence. And also, if the interleaving is non-additive, then there are no bits being added. So basically, by sending all zeros, these two stages fall away. We don't have to worry about them, and the only other thing that we need to control for is the gray indexing. So there are just 3 different states that we could try: graying, no graying, and degraying. And then when we get the zeros out, we know we got it right. So that's how we were kind of able to solve for these first 2 steps, the gray indexing and the whitening, kind of in one go. All right, step 3, finding the interleaver. There was an interleaver defined in the Semtech European patent application that I mentioned. And it suggests a diagonal interleaver abiding by that formula there. Guess what? That also didn't work. Fantastic. So we're 1 for 4 on documented features right now. The gray indexing was actually degray, like the inverse before it got sent. The whitening algorithms that they gave us did not work. I still have no idea what those algorithms are applied to. They're in the documentation, but they're not what actually were actually implemented in the PHY. And now the interleaver that's in the patent is not the one that's there. So we're going to have to figure this out experimentally. Okay, so deducing the interleaver. This was hard. This was the hardest part of all this. Bear with me. I have some graphics that I think will make it a little easier to understand. But just like we did with the whitening, we're going to exploit properties of the Hamming forward error correction to get the interleaver to reveal some patterns about itself. So remember that most Hamming code words contain 4 set bits except for 0 and F, right? So 0 contains no set bits. F, all the bits are set. So if we if we craft transmissions that are all zeros except for one set of Fs, and we walk where the F is through the packet, we can start to reveal some properties of the interleaver here. I'll make it easy for you. Does anybody see what's happening here? So I'll draw your attention to the bottom row, second from the right. That's the payload for 0F and then the rest zeros. And you can see that it's almost perfectly diagonal, right? And if you look at the other ones, you can see that it's also similarly diagonal with an offset. One other thing that I'll call your attention to is that the most significant bits in each interleaver block are flipped. So, looking at the data it didn't make any sense until I constructed these payloads to try to back this out. And this was the first step to start seeing the patterns here. Okay, so with this, we've mapped out which diagonals correspond to each 4-bit positions within, or to each of the bit positions within the transmitted payload. So with that in hand, we need to think about aligning each of those code words within each diagonal, right? So we can map the diagonals to the code word, but the bits that we get out of each code word are scrambled around. So we need to start looking a little more granularly into each of those diagonals to figure out what's actually happening there. So our solution, again, just like before, is to transmit some known words and look for the Hamming FEC encoded signals within each diagonal. So we'll take a known, well-loved known payload here, and we will map out the diagonals into a table. You guys see what's going on here? Basically, we know the diagonal position from that exercise that we did before. So we're just reading each position that we know from where the F was into this table here. We populate this little matrix here. And here it is next to the data that we're expecting on the left, right? So we have the unencoded data in the middle column there, and finally the parity bits that we expect to be applied to it on the right. Does anybody see anything here right off the bat? This might be a little bit harder. Again, I'll make it easy. Oh, wait, no, sorry, jumping the gun. One thing so just to help us along here, if you reverse the endianness of this, then you start to see patterns here. So here, we've got the data that we find in these bit positions here. And if we go a step further, we can start to correlate and map some of those Hamming FEC fields into these interleaver code word positions. So these 6 fell out pretty nicely. Interestingly, Hamming parity bits 3 and 4 were flipped, and that's something that was just deduced experimentally by looking at the actual values versus the expected parity here. So that's a huge step. We're almost there. If we apply the forward error correction to these bits that we have here, we've got it. That's it. That's the whole thing. So that's the phi. We just went from that weird, diagonal chirped, modulated signal to the data that's in there, just based on some open source documentation and gumption. So how are we able to do this? So we have these 4 steps, right? And I hinted at this earlier, that we were able to control for the first 2 and make an assumption about the last step, the FEC, based on some documentation that were leaked. And basically what that meant is that the only experimental variable that we really had to solve for that was really hard was the interleaving. But since we were able to control these other 3, then we only had one variable that was unbounded, and then we could solve it. It's like algebra. Okay. So what's next? You guys want to play with this, right? You guys want some tools. I'm working on that. So I want to briefly introduce GNU Radio LoRa. It's an out-of-tree GNU radio module that implements the LoRa PHY. I'm working on it currently. It's going to be released between now and GNU Radio Conference in September. So this will be out there. You guys can grab it, play with it. It's going to have GRC and all that good stuff. I have a proof of concept receiver complete. I just got the time warning. I don't think I have time for a full live demo, but if anybody wants to see it, I will be happy to show it to you right after this talk. So finally, to conclude, these LP WANs have a ton of momentum and are rapidly proliferating. I mean, you're going to be seeing these everywhere with all the money they're raising, with how how much everybody's emphasizing IoT. It's inevitable. These things are going to be everywhere. One other point I want to make is that RF stacks are becoming more diverse, right? When you think about wireless, oftentimes in the enterprise we think about 802.11, but wireless is not just Wi-Fi anymore. You have to start to think about these protocols, Bluetooth, the cellular. It's all out there, and it's all starting to become connected to the internet and more interrelated. Third, we've shown how to go from some obscure RF signal to bits, and fourth, we're adding a new tool to the RF security researchers' arsenal, so you can start to take a look at this brand new network that is totally greenfield and start to find things and make it better. Finally, I want to acknowledge my team at Bastille, especially Balance Sieber for helping make this happen, the open source contributors for starting to look at this, and the Wireless Village for hosting. Thank you very much. I'm happy to take your questions. Okay, so the first question is, have I heard from the company in question? And I actually have. So, I first published this research back in May, and not too much happened. But finally, I did get an email from one of the guys who worked at or from one of the founders of the startup that invented this modulation that was bought by LoRa. So the guy that invented LoRa shot me a note and said he thought it was awesome. So I haven't gotten any C&Ds or anything legal, but I did get a digital high five from the guy that made the PHY.
You said that the gray coded data was transmitted. Does that mean that your gray coding is not being applied at all?
No, it's being applied in the inverse order. So yeah.
So given that there's like a carrier sweep across the band, can like two LoRa channels sit on top of each other?
That's a good question. I actually haven't looked at that because I only have one radio. Yeah, I did do some look at some basic jamming. LoRa is really good in contested channels, so even just using a usurp on max power, I wasn't really able to jam it with wideband noise or anything. I really wonder what would happen if you were to stack a whole bunch of LoRa carriers on top of each other, if that would just totally throw a receiver out. Yeah, exactly. Just imagine just drawing diagonals all over the 900 megahertz spectrum.
And the other question was there any particular reason you didn't do like a quadruped modulation instead of using the...
Would that work for MFSK? Basically, the whole point of dechirping is that it converts those signals from the chirps to those nice linear pulses, so we can basically treat the whole thing like multiple frequency shift keying.
Sort of. It would give you like the lines in time, but then you could do like a derivative filter on it to get things out.
No, I hadn't thought of that.
Okay. Where can you get LoRa hardware?
So hardware's out there. You can get dev modules on DigiKey. They're not too expensive. Of course, ICs are available in volume, but honestly, like there are more and more signals in the wild. I mentioned I had that slide about my road trip to Portsmouth. I had to go to the source to find it there. I see LoRa everywhere now. I actually haven't checked here in Vegas, but all over Boston, all over San Francisco, it's popping up. So it's out there.
Mainly being used for like industrial type stuff, like monitoring applications, or is there like consumer stuff using it yet?
So it's kind of all over the board. I mentioned the heating oil company Senate that it's monitoring gas tanks in New England. I think there are people doing vehicle fleet monitoring, just reporting GPS and things like that. One really interesting case that I heard about, I met this guy at a conference who he was making 802.15.4 connected rat traps. These are things, I know, right? IoT, woo! You put these things in your crawl space or whatever, and it used a thermal sensor to detect when a rat had been caught and actually killed, right? It looked for like the temperature going down to room temperature. This is a real thing. I'm not making this up. But yeah, so he had made that on 802.15.4 and Zigbee, and he was psyched about LoRa and couldn't wait to make LoRa connected euthanization for rats. Anyone else? Okay, I'll be around. Come find me if you want to talk about this. Thanks again.
Okay, thanks, Matt.